my name is Scilzo. I'm an adjunct professor at Jackson College, and today I would like to teach you how to read a basic stress-strain diagram. Now, those that might be familiar with a stress-strain diagram might see that this is for a ductile material. If we were talking about a brittle material, this curve would be much straighter, and the difference between what I'm sure is ultimate strength and break strength would be much closer. But again, we're going to be talking about a ductile material. Now, in a previous video, I defined what stress and strain were. Now, I'm going to show you if we plotted one versus the other. We can see that strain is on my x-axis, stress is on my y-axis. Okay, so obviously this is the independent, this is the dependent variable. Now, along that line, this is the original line that I'm showing you here. This is the actual line. If we actually pulled that sample that I showed you and actually pulled it to the point of breaking, this is what the curve would look like. We can see that we start at the point of zero. We have zero stress, we have zero strain. We pull all the way up to what's called proportional limit. Now what this means is that during this period, we have a linear relationship between stress and strain. And if we wanted to find the relationship, we could find that as E, or this is called Young's modulus, is actually equal to stress over strain. And you can see in a linear proportion, and this would actually be the slope of this curve between 0 all the way up to the proportional limit. Now, on most ductile materials, this will stay very close all the way up to the yield strength. So we can see what is the yield strength? Well, if we in fact would pull this over by 0.002 or 0.2%, we would see that we develop another point called the yield strength. Make sure you understand this is not a stress, this is the yield strength. This is the strength of the material. And this is actually what we use most of the time, because we will pull this and find this yield strength and use this for our factor of safety, which I'll talk about in the next video. Now, so in this area, if you would pull all the way up to this yield strength, your material would go back to its original shape. If you go beyond this point of its yield strength, as soon as you pass this, you are in what they call the ductile region. Let me write this in. This is called the elastic area, the elastic, and this is called plastic. And when I say plastic, this means from this point on, if you pull the material, it will permanently deform. So if you think about a paper clip or something, when you bend it so far, it permanently deforms. Well, you have passed your yield strength on that paper clip and are now in the permanent deformation area, or the plastic region. Now, again, let me just define stress again. Force over area, and it's normally in English units, pounds per inch squared, or PSI. The strain is actually unitless. It's in inches per inch. It's actually defined, if you remember from the previous video, as delta over L0. And if you can go back and refer to one of my previous videos if you're not sure what that means. So again, that's our first point, our proportional limit, excuse me. Our second one is our yield strength. And finally, we're talking about our ultimate strength. This is the highest point that our strength that the material will see. Now, it will continue, it actually continues to go up like this, but it's deforming so fast that our fracture point is actually down here. So this is actually the way that the curve would actually look. If you did this on a tensile tester, and that's how they check all the materials when they want to see what kind of strength they have. And every material in the world has a different stress-strain curve. So again, this is our elastic region. Everything in here will go back to its original shape if you pull it all the way up here. From that point on, you will have a permanent deformation of your material. And this is basically how you would read the stress-strain curve. Again, all the way up to proportional limit, this is where Young's modulus, E, is valid. This is your slope between your stress and your strain. Rise over run, if you remember from your old algebra classes. So again, and from this point on, it's permanent deformation. So I hope that gives you an understanding of what a stress-strain direct diagram looks like. Thank you very much for your time.